All right. Hello. Welcome to the Off by One security stream. My camera is not working today. I don't know what it is that's not letting it work, but I'm kind of jumping on here last minute. So I'm not going to reboot and just try to get that working. It's fine. Just a couple quick notes. So I've got a lot of streams coming up planned, as you probably saw if you're keeping tabs on it. The next 4 weeks after this are booked out, and I've got a couple guests that I'm talking to beyond that as well. And there's some really cool streams coming up. I've got Anuj Soni coming on to talk about Ghidra and using Ghidra to reverse malware, amongst other things, because I know some folks have been asking for Ghidra because I show a lot of IDA Pro. And then I also have one of the developers of Binary Ninja coming on. So he will be giving away a license to Binary Ninja to one lucky person. That'll be coming in a couple weeks. You can check out the schedule. I've been posting on Twitter as well. So we've got a new Sony for Ghidra. I've got one of the devs from Binary Ninja to come on and give away a license and show us Binary Ninja and the great things you can do with that disassembler and decompiler and debugger. And then I've also got uh, the developer of GEF coming on to talk about how that GDB extension works for exploit development and all the great things you can do. I'm looking forward to that one to learn a lot of new tricks that I maybe don't know currently. And then I've also got Kuba Gretzky coming on. I think that's March 1st. He's going to be giving away 3 seats to his course on bypassing multi-factor authentication using Evil Jinx. So some great giveaways. Also, I was talking to Hexrays, who makes IDA Pro, and I'm going to be scheduling one. They're going to give away a license to IDA Pro, so one named license for that, and that's an expensive tool, so that's a really great giveaway. And they're also going to send some swag my way, so hopefully I'll have some other cool things to send out. So I was going to do an IDA Pro session for this one, and that's what I was planning on doing, but the fact that Hexrays got back and said, "Hey, we want to give away a license," I was like, "Well, let me put the brakes on what I wanted to do, and I'll schedule that for the future." So I wanted to have something to do today, and I kind of was falling apart. Not falling apart; it doesn't make sense. I was falling behind. That's what I meant to say, and didn't have anything on my mind. But I posted last week or earlier this week. I don't even remember anymore. I think it was earlier this week. A session on yeah, I was talking to Richard Johnson quite a bit back and forth. He's really busy, and we were going to do a session on fuzzing. I reached out and gone back and forth a couple times. I don't want to keep bugging somebody if they're just too busy, so I'm kind of waiting for him to reach out back to me. But if he is not able to jump on soon, I do plan on doing a smart fuzzing session regardless. And I don't know if I want to use WinAFL and or Frida and or what exactly I want to do, but I definitely want to show some of the latest stuff with Dynamo Rio and the block instrumentation that you can do, whether or not you have the source code or you just have a closed source situation. Yeah, for sure. I definitely want to do fuzzing. So those are all the great sessions coming up. But as I was saying, I released a video, I think it was earlier this week, on creating flirt signatures. And I got quite a few questions on that one. Some on YouTube, some on DM via Twitter and other ways. And some folks were asking, well, how was the question specifically? The same question came up a few times, which was, how do I know the version? Because as you can imagine, with libc and all the different modules, all the shared objects out there, and I mentioned libcrypto and libssl, and there's a ton, right, of open source libraries out there. And obviously, these things get updated all the time, thus recompiled all the time, and things get moved around. Obviously, the addressing changes, the offsets change, other things change. And I was mentioning how you end up with a giant flirt signature database if you want to do it right. And I was saying how I remember many times doing the DEF CON CTF prequals, and you get a binary to download, and then they give you an IP address of a remote system. Maybe it's one of the potent ponables or whatever they're called. You can connect to it across the net with Netcat or something like that, and it prompts you, and it's just a little CTF challenge. And they give you a copy sometimes so you can download it, because obviously you've got to be able to do your reverse engineering on it locally typically. And sometimes you don't know what libc version they're using on their end, right? Like it'll still work on your system because you've got the libraries and things you need. But let's say you get something like a memory leak and you get it working on your system, but you don't know the remote systems library versions, so that even though you're leaking out an address, you don't know what the right relative virtual address offsets are. So if you're building a ROP chain or something like that, or a one gadget, you don't know the offsets because you don't know their library version. So there's a trick you can do. This is nothing new. It's just CTF gamers know about this very well for the longest time. It's a tool called libc database. And let me put up the thing here real quick. I'm going to put it in as a comment, and I'll put it on the screen as well. That right there, that's the group that created libc database. And I'm going to use that in this session to kind of show you how it works real quick. It's a real neat, simple tool, but it's very helpful. When you combine this with flirt signatures and things like that, like all this stuff improves your gaming chops. And it's not limited to CTF, but things like pwn tools and libc database, and like a lot of those things were designed by CTF teams or developers to better their game. Obviously, they can also be used in the real world, but a lot of the stuff, again, is designed for that. Things like one gadgets, for example, those are really useful in CTF challenges too. If you're familiar with return-oriented programming, then you know that you typically need to build a ROP chain that's a bunch of different pointers to addresses, which contain short code sequences that when you string them together and get them all executed, you accomplish your goal of messing with mprotect on Linux or calling virtual protect on Windows. Um, a one gadget is a very special gadget that it only takes one gadget. If you can get code execution and redirect execution to that address of the one gadget, it pops a shell. And it's great for CTFs. And almost every version of like libc.so.6, for example, has one or more one gadgets in there. So again, you get control of the instruction pointer, you redirect execution to the one gadget, you pop a shell. It just happens to be a magical gadget where it lines up /binsh to execve, and you're good to go. So stuff like that is really cool for CTF games as well. Again, if you're just joining now, my camera's not working right now. That's why I'm not on the screen, and I don't want to reboot my system because then it will drop. So let me get to the point here, because I again wanted this to be a rather short session. Yeah, I'm happy to take questions as well. But so I'm on a VM that I use in 760, which is a course that I'm one of the authors on at the SANS Institute. And a lot of times, like some of the sessions that I've done have been on retired content that I still think is really useful. For example, some of my favorite content that I've done on this channel is the browser exploitation stuff. Like when that was hot, meaning that when it was 2014, 2015, around that time where use after free and type confusion, and then these browser vulnerabilities, they're not limited to browsers, but they were big in that space. You would only need, this is the beauty of it, you back then in 2014 only needed one single vulnerability and corresponding exploit, and you win. There probably wasn't sandboxing, at least not with Internet Explorer. I'm sure on Chrome there was, but like not on Internet Explorer, and that was popular in enterprises. And so no sandboxing. And there was this library, speaking of libraries, that came out. It was part of Java Runtime Environment 6. And I remember the library name because it was infamous. All of us who were doing this exploitation back then, it's msvcr71.dll. It was not participating in dynamic rebasing. It had no protections on at all. So, and everybody had Java, right? Everybody had Java runtime environment installed. So you could change the terminal block on your blind. All right, these are first world problems here. Let me see if I can change it real quick. Um, so you back then were able to get a single exploit and you won. And that module was not participating in mitigations. So it was just simple. And you were getting paid a decent amount of money for this stuff. I don't remember what the option is here. No, that's not the right thing. That's for the preferences in here. I don't remember where they are in this particular VM. Let's see if this is going to work. How about white on black? There we go. Is that better, hopefully, for now? All right. So as I was saying, that was my favorite content to release because it was super, super useful. And I decided to release it on this channel because it still is very useful. I mean, we go through the process of looking at a browser memory leak and weaponizing it and how you go about modifying the size, because like the particular browser exploit that I released, the second one that I did, it was against Internet Explorer 11. And the neat part about it was a use after free, and you could control the size of the allocation, which is basically the internal or inner HTML of an object, of an element. And based on the size that you created this text string in that case, when it got freed because the memmove function was being called, there was basically a realloc call occurring. Because if you go and change the size, let's say it was 40-byte text string, and you change it to 3-byte text string, for optimization and to, like, you know, save on resources, it would call realloc to then allocate a smaller allocation of memory so it could free up the prior allocation that was large. So it makes sense, right? We don't need all that space, so let's free it and let's only use what we need, and then we can recycle that old memory. So that hole that you were leaving due to the vulnerability, because basically pointers were not getting updated accordingly. And so when that hole would be left behind, something else could use it. Something else being, you're running a browser, something's going to take up that old memory real quickly. Now, if you want to have control over it, the way it used to work, it was last in, first out. So basically, if you freed something or got something freed, immediately the next allocation that is, around that size would use that freed memory that you're involved in. And so you could customize kind of based on the hole that you're punching. You could then allocate something immediately or create an object immediately and its attributes, and it would fill that slot, that hole you left behind. So it's like that kind of stuff is really, really useful, regardless of the age of it, which is why I released it. So anyway, I went on a little bit of a tangent there. Basically, I was just saying that some of the content that I do post here with these videos is is um is going to be from some courses that I've written that maybe the content has been removed for one reason or another, but it's still very useful. I posted on Twitter or X, whatever it's called, a blog from Exodus Intelligence, and those guys are amazing on exploit development. And it was an exploit against the Java V8 version V8 on Chrome. And man, it is a amazing exploit. I read through it pretty quickly and I realized that this is not going to be a quick read. So I went through and slowly digested it and spent a few hours kind of really going in and Googling some things that I wasn't familiar with. And man, it is an amazing exploit. And like that is a real good example of modern browser exploitation compared to 10 years ago. It is night and day. It was so easy back then. Back then, it wasn't easy. And if you're new to it, it's not easy. But versus what you have to do today, it's quite a difference. This is again why so many people go off and say, you know what, I'm done with kernels. I'm done with browsers and stuff like that. I'm going to go after cars and IoT and just new attack surfaces that need attention because history repeats itself and we end up making the same mistakes that were made over and over again in the past. So yeah, I saw the question many times. Hey, can you make a course from crash to the advanced level? Yeah, I mean, I do have courses that cover that kind of stuff. I know that sometimes the price tag can be hefty on some of these courses, but yeah, I do plan on doing more sessions here as well. Like a lot of people have been asking for fuzzing because a lot of courses out there will start with, okay, we've got a vulnerable crash condition, let's weaponize it. And that's super useful, but finding those types of crashes are a big part of this, right? You've got to find a vulnerable condition, a bug that causes a crash. You got to look at it post-mortem to see whether or not it potentially is exploitable. Then you got to start debugging it, reversing it, and determine if it is in fact exploitable. And then you've got to try and weaponize it, compensating for any mitigations and heap grooming and everything else. So it's quite the process. A lot of people keep that stuff close to the chest, though. I know I use that saying a lot, but it's true. Like if you look at iOS exploitation, if the vulnerabilities, if the exploits are worth millions of US dollars, people aren't going to share that stuff for free. So when somebody finds a new fuzzing technique or a new attack surface that they're doing something that's having some really good success, they're often not going to share that until it's no longer getting much return on investment. which is understandable because this is people's livelihood. But yeah, it is important though. Like when I was doing browser fuzzing, I stopped doing it for the most part because it's just the return on investment isn't there as much as it used to be. Because with the controls like memgc and deferred free and isolated heap and control flow guard and all these things, VT guard, virtual table guard, it ends up making it very challenging to exploit a vulnerable condition. So the vulnerability is there. The code is in fact vulnerable. Microsoft or whoever it is will fix the code and the bug, but you just can't exploit it anyway. So yeah, you'll do a patch diff or something, and you'll see that this is an exploitable condition, but due to the mitigations, you can't exploit it, and that's very frustrating. So when something gets extremely hard, obviously the investment in time to go in and try to weaponize a crash condition is extensive. And then often you'll find that you can't actually exploit it. So a lot of us will jump around to different attack surfaces that end up being more rewarding. Not to say that there's no shortage of browser vulnerabilities out there. There's tons of them. It's just exploiting them has become really hard due to the mitigations. But the price tag is much higher. I would imagine, and I haven't sold one in a little while. I haven't sold a browser exploit in a few years, but I would imagine that right now, if you got a full chain exploit against Chrome, and that would include the escalation and sandbox escape and memory leak and code executions, like 4 bugs strung together exploits. I would imagine that's worth at least $500,000. I mean, I wouldn't want to sell it for any less because that's going to be an extremely big time commitment, right? So anything else? Linux rootkits. Yeah, that would be awesome. I was talking to my friend Oscar Tejeda over in Dominican Republic, and we were looking at a course to write for SANS actually that was going to be on Linux kernel exploitation. That would get into a bit of that as well. Jonathan Ryder, who is a guest on my stream a couple of times, he's the author of the course on writing basically red team tool development on Windows to write your own implant in userland. And he does a lot of stuff in the kernel as well and wants to write a course on kernel implant creation, which would be quite advanced on Windows. But similarly, you could do the same on Linux, of course. So, going to say a few words on VM escape exploits, layout, and such. That would actually be a good one to have somebody come on and talk about. It's your attack surface there is obviously when look at like VMware tools, for example, like anything that or file sharing. I remember there was an old file sharing vulnerability with VMware that you could basically get something to execute on the host based on that file share. It was an issue there, but a lot of that has to do with, again, whatever attack surface is brought in between the virtual machine and then the hypervisor or VM application that's controlling it. That's obviously what you're analyzing. Kind of like with virtualization-based security, this is a big area because if Microsoft can, they obviously are going to continue down the path of uh, VBS. I just saw that. I think Conor McGar posted it. They extreme control flow guard or extreme flow guard just got deprecated. Thought that was interesting. But anyway, the like from a high level, you've got ring -1, which is Hyper V. Take credential guard, for example, where the LSAS process is still there in userland, but now there's a separate secure kernel with an isolated user mode process in a separate ring 3 that's got a different version of LSAS that's called something else like LSAIO or something, and it's encrypted. So in other words, it kills Mimikatz, right? You use Mimikatz in userland on the primary operating system, and there's nothing in there. You get no results. So in order to get to LSAS, there's obviously a broker. There's some way that you're able to go from ring 0 in the kernel of the main operating system through over to the secure kernel via the hypervisor. And then there's protections and such. There's a broker there that's letting you through. So that's your attack surface. So like it's similar with the VM escape stuff. You've got to identify what is it that has been injected. Like another silly example, I was just I forgot that I installed this on one of my computers, this tool called Camtasia, and it's a screen recording software. And it injects DLLs into every single process that you start up. Like stuff like that is some of the stuff you're looking for as well. Like that's kind of annoying and scary that there's DLL injection basically going on into every process that you start. All right, so let me get back to the point of this. We could chat a little bit more afterward, but the point of this is identifying library versions when remotely hacking Linux vulnerabilities or in relation to flirt signatures like we were talking about earlier in the week. So this is a VM where I'm just going to look in the folder because, again, I just kind of randomly decided to do this stream. So I've got this program called Baby Sec 760 Heap. This is a kind of optional challenge that you can do in the course if you want to during the bootcamp extended hours. And during the daytime of this particular section, we talk about exploiting Tcache vulnerabilities or messing with the Tcache bins and exploiting relevant vulnerabilities that allow you to kind of utilize the behavior of the Tcache bins to for optimization to get what you want. So this is just a extended hours kind of optional challenge you can do for fun, and we give you the leak. So in one of the exercises earlier in the day, you have to find a memory leak, and basically you do that by a lot of times when stuff's being allocated, chunks of memory on the heap are being allocated and then freed. Memset is not being called to clear out the old data. So what you can do, since that's your chunk that you've allocated, oftentimes you can read what's there. And what's there might be pointers or memory addresses, which are offsets to things. So if you can identify that when you do an allocation, and if you look at the contents before you overwrite any old data that was there, since memset hasn't been called, if you look at it and you see that there's an address, you can look at that address to see what it is, what's there in a debugger. And it might be some relative offset within a module or shared object or library. And with that can be a memory leak now because you can subtract the relative offset to get back to the base address, regardless of the version of the module, or I should say, regardless of ASLR, is what I meant to say. So if rebasing or randomization is occurring, what you're leaking out, the address might change, but it should just be the base address that's changing. The relative offset should still be the same. So that's how we exploit memory leak vulnerabilities to determine the base address so that we can utilize relative offsets for ROP chains and the like. So in this particular one, I'm going to show you we give you the leak address just to save you some time. But earlier in the day, you're working with trying to identify leaks yourself. So if I run this little program here, Baby Sec 760 Heap, you can see it says, here's a gift from me and Wasker Tejeda, and it gives you two addresses. So you don't know what these addresses are. We're giving you that as a present in the challenge. So kind of to move you further along, because the goal of this particular exercise was not for you to figure out how to do memory leaks. We already did that. It's for you to practice doing Tcache poisoning. And Tcache poisoning, if you're familiar with Linux, it used to be that there was a main arena. We call a heap on Linux an arena. And on Windows, you would call that the process heap, right? Just a basic process heap that kicks off when you start up. And on Linux, obviously at some point, instead of forking all the time and creating child processes, we can utilize threads and such when needed. It's not always the same thing, but most of our applications now are multi-threaded, of course. And there's a global mutex that gets passed around. I'm sure you're familiar with mutexes and spin locks and such, but we're trying to prevent, let's say, two threads from accessing the same thing at the same time, because that could be problematic. So we have a mutex. You can't do anything unless you are owner of that. And then when you release it, then somebody else can take it over. So to optimize, they started creating multiple arenas. So each thread on most operating systems, when a process is running, each thread gets its own stack. So its own stack-based memory is given to it. And there's a bunch of other stuff that comes along with that. But historically, each thread was not given its own heap. But if we've got enough memory and we do things right, and the heap manager, like TC malloc or whatever you're using, supports it, then why not give each thread its own heap in each process with virtual memory? So there's a little calculation depending on if it's 32 or 64 bit, but you can do a multiplication of the number of cores on your processor times a certain value that's basically compiled into the malloc implementation that you're using. And that would tell you the number of heaps or subsegments and such that you can use. Um, each one of those threads then doesn't have to wait for this global mutex, right, that's being passed around, because it's got its own stuff, including T-cache bins, thread cache bins. And that's all. Like, if you're familiar with the heap in general, there's front end allocators and then there's back end allocators. And the front end allocators are supposed to be faster, and they are faster to get an allocation from it, because we don't have to like worry about fragmentation. For as an example, on the backend heap, there's a rule that says no two free chunks are allowed to be side by side and free. We coalesce them to reduce fragmentation. But on the front end heap, such as Windows low fragmentation heap, they typically service commonly requested or small sized chunks of memory. And I've given this example many times in the past. Like, if you use a browser and you look at the HTML of a web page, you're going to see lots of divs, span, tables, buttons, titles, all these elements that are common. So those elements have a static size associated with them. If you were to look at the C++ class for something like cbutton, there's going to be a create element function that has a static size associated with it. So that element or object has a static size. Now, you may say, well, what about the inner HTML or the text around it? That's different. Or what about the attributes, like the coordinates around an area element or a shape? Well, those are attributes. That's different. Still, the element itself will have a static size. My point for saying that is those are things that'll be serviced by the front end allocator, most likely, because we know that you're going to constantly be requesting them. We don't worry about fragmentation, because as fast as you free this stuff, we're quickly allocating and requesting them again. But if we have to go to the backend allocator, that's going to be a little bit slower. Like on LFH, I don't know if it still works this way. I imagine it does. That's the low fragmentation heap on Windows. Um, I know, like in the kernel with LFH and the segment heap, that LFH is just on by default, but it used to be that you would have to have 18 consecutive allocations of the same size to turn on LFH to service that particular size on that heap. And but even if a request was coming in and LFH was turned on for that size, you still go to the back end first before you then get told to go on the front end. Like on Windows, there was a little variable in there that said 2. The number 2 meant LFH enabled, 0 meant LFH not enabled. And then the backward pointer of each doubly linked list pointed to a counter, and that counter was watching the number of requests for that size. So anyway, I'm going down a rabbit hole that we don't need to go down. Just talking a little bit about the heap here. So let's jump back into here. So we get these two addresses given to us, and we don't know what they are yet. And the point of this is to show you how you identify the libc version if you don't know what it is. So that's going to be our goal here. One thing before we continue down this path, earlier in the week, I told you, and maybe you checked it out, there was a video on using flirt signatures, creating flirt signatures. And I created this program up here. It says baby sec 760 heap stripped, and it's statically compiled. So if we look at file baby sec 760 heap, it says it's stripped, but it's dynamically linked. So that means it's not statically linked. That means if you run this program on your computer, you need to have the dynamic dependencies. So if we say LDD on baby sec 760 heap, these are the dependencies, the modules that you need to have for to be able to run my program. But if we look at the other one, so if we say file baby stripped, it says statically linked. So that means the modules have been statically compiled into the program, which makes it much larger and adds confusion. Now, one of the things I didn't do in the video earlier in the week was I basically just statically compiled libc.sharedObject into a binary. And I showed you that it was much, much larger. And if it's stripped as well, you've got hundreds and hundreds of functions that have nothing to do with the functionality of the program. The one thing that I didn't do that you would normally do is you would statically compile the libraries that the program actually does need, because that makes things even more confusing, because there's going to be calls to functions that are the statically compiled library code and you don't know what they are, which is where the flirt signatures come into play. So anyway, we know this thing is stripped. I just want to point out one quick thing as an aside here. That's why I'm showing you this one. And that is, if we run this version, notice that it says nil and then this address. But if we run the other version, it shows totally different addressing. Well, that has to do with the fact that the one on the top was statically compiled, so it's messing things up. But what if you want to find the main function in that example where it's statically compiled and stripped? I went over this a bit on the other video, but let's take a look at this one here. So if we say GDB baby heap stripped, and I say info functions, it doesn't give me anything, so that's not helpful, right? Well, one problem is there's no, it's stripped, and there's no dynamic dependencies here. Normally you would have it here, and I'll show you on the other program. It would say something like call printf at procedure linkage table, which is how the Linux binaries are going to go through and link. So that makes things challenging. So if I say disassemble main, there's no symbol table, it doesn't work. So how do I find out where a main is? Couple ways we can do it. One way I'm going to do it is this way. Like if we say read elf minus a, and we say I think it's capital, I don't remember, baby sec760 heap stripped, and we grep for entry, it's going to be lowercase a. So we get the entry point address right there. So that's helpful because that's going to basically be start. And start is where the program's going to, you got it, start. And pretty quickly inside there, the logo's blocking the command line. What logo? Oh, that big thing. Oh, let me get rid of that. Sorry. Hide current comment. There we go. So like it's not on my screen, but then I'll look at your screen. I can see it. So a few commands or instructions down is going to be where the arguments are being loaded to call libc start main, and main's going to be the third argument passed. So there's a couple ways we can do this, but one quick way is this. If we take this address of the entry point, and then we just say something simple like obj dump minus d for disassemble minus j for section dot text for the text segment, the program, and then we say grep for that address minus a for the number of lines after, and I'll put 10, we get this. And right down there at the bottom end up being the perfect amount. There's the call to libc start main. This right there, this address right there is main being moved into RDI. So we can take this address now and we can say, let's go into, if you can hear my dog in the background, I apologize, he's freaking out there. We can now say examine, let's say 8 instructions starting at that address. And right there, you can see the procedure prologue. So that's main, which makes it nice because then we know where we are in the program. Same thing with using IDA Pro or Ghidra or Binary Ninja or whatever, Hopper. You can do things similarly. But just a quick one. So finding the entry point on Windows. Oh, there's a ton of tools for that. Oh, what's that one? PE Studio is a good one. It's a portable executable studio that shows you the entry point. It's a GUI that you can run. It's free. So let's drop out of here because that wasn't the point of this. And let's get to the actual point. So now I've stripped the other one. The regular baby heap program has been stripped as well, which means there's no main. But I'll show you one thing real quick. It should be in there anyway. In this guy, if we say info functions, right there, you can see all the dynamic dependencies. So those cannot be stripped unless it's statically compiled, because you wouldn't need them. But because these are dynamic dependencies, like my program, if you run it on your computer, has to be able to tell your loader and such, your linker, what functions the program needs, and it has to be linked. So there might be a protection called relrow, which is relocation read only, or there might not be. There might be lazy linking being used. Either way, when you go to call one of these functions for the first time and it hasn't been linked, it's going to call the dynamic linker, and the address of the function within the right library is going to be written to the global offset table entry for that given function. All right, so we are here to look at this leak. So let's go back up. Let's go ahead and run it. And if we run it right there, it says, here's a gift, and those are the two addresses. So let's take this second one first. That's a weird address, right? Well, there's something called position independent executable, pi. Pi is the randomization for the binary itself. If you turn on the flag in, what is it, kernel sysproc, I think it is, randomized VA space, there's a flag in there, 0, 1, or 2. That's going to randomize, if it's a 1 or a 2, it's going to randomize the stack and the heap and the libraries. That's a big difference between Linux and Windows, right? On Linux, ASLR randomizes the libraries every single program invocation. Every time you start the program, the libraries are rebased. Unlike on Windows, they're only rebased once per boot, because the way in which for efficiency and optimization, the library is shared between all the processes that need it, which is why hot patching and such gets complicated. But on Linux, it's less, I guess, performance concerned, and it randomizes the library with every single start of the program. So either way, I'm going to take this address, and if we say copy that, and I'm just going to say examine 8 instructions starting at that address. Oh, I need to pause the program first. So examine 8 instructions starting at that address. And you could see we're at the procedure prologue of something. If you're not familiar with what the prologue is, that's every stack frame has a prologue and an epilogue. So it's dynamically inserted code by the compiler based on the calling convention and such, where every time a function gets called, a stack frame needs to get built. So the prologue is what builds the stack frame, and the epilogue is what tears it down and then returns back to the caller. So we see the prologue of this function. It ends up being main. It's stripped, but it's main. How do we know? Well, we can easily just do the same thing I showed you before, which is look at the entry point and look at start and see what arguments being passed to libc start main. So that is main. So we're giving you in this challenge the address of the main function just to make it easier for you to find your way around. And then the other function that you're given, if we restart this thing to make it easier, is this guy. So we'll take this address and we'll say examine GX, because 64-bit stands for giant. Paste that address in. I forgot to pause again. x/GX. Paste that in. And you can see it's the address of freehook. And the interesting thing about freehook is that these are heap debugging routines. And notice that it's set to 0 right now. This is one of the really cool things about one of the cool techniques on exploitation on Linux, is that similar to like CTORs and DTORs, how there's like a little check that says to see whether or not there's code that needs to be executed before we pass control to main or while we're exiting. Freehook allows developers to debug their program and basically get it's almost like you're hooking, basically, right? You're getting a first shot at doing something before it actually goes and executes the code in free. There's malloc hook as well. So there's multiple hooks. And if you can get something written to the address of freehook, when free gets called, whatever address you have there is going to get code execution first. So that's pretty nasty, right? So like in capture the flag challenges, what they'll often do is they'll write the address of a 1 gadget to that location. Let me show you a 1 gadget real quick, what that looks like if you haven't seen it before. So if I say, you notice inside of here, we got a version of, oh, we don't in this guy. I know we do in another location. Let me see if I can just copy it over here real quick. So copy / baby sec baby heat libc.so to here. Okay, now I got it here. So if I say 1 gadget libc.so, give it a moment. Look what comes up. These are examples of one gadgets. So in other words, this relative offset within this specific version of libc, that's the big point I'm making, that's only relevant to this version of libc. And that's the question I was saying. The reason behind this webcast, this stream, is how do we know what version of libc it is? Because if I'm using this version of libc, like let's say, let's put this together. If I'm doing a capture the flag challenge and there's a remote system that I'm supposed to exploit, and I download a copy of the binary and I run it on my system and debug it, and I find the vulnerability and I've got it working on my system, great. But I don't know what the libc version is on the target. So if I use a one gadget address or any gadget address, it's not going to be right. It's going to be the wrong address unless I'm really lucky. So a one gadget, again, these are the constraints, which means that you would set a breakpoint on this address when code execution occurs, and you would validate that those constraints are satisfied. And it says either whatever address is stored in RCX, it needs to be pointing to a null, like what's stored there has to be 0, or RCX has to hold a 0. If either of things is true, then great, you pass that constraint. The other constraint is below it. It says the pointer to the pointer, right, to RBP minus hex 70 has to be pointed to null. What's stored there has to be null, or just the address in RBP, or whatever's at RBP minus hex 70 has to point to a null. Like if those are satisfied, then you're good to go. That one gadget will work. And if you look at that address in memory, you would see that the code calls execve and loads the arguments for /binsh, everything that's needed to pop a shell. Let me see if I can show you that real quick. I'm going to grab this address right here. I'm not 100% I'm going to be able to show you. I think it's the same version for this one, but let me run the program. And we'll say run, and I'm going to force a break via map. I'm going to look at libcso real quick. So libcso is loaded at this address here plus that offset. So let me paste that offset in first, and let's grab that address. So home, let's see here, examine 4 instructions starting at that address plus this offset. That did not work out the way I wanted it to. So the offset's going to be different. That doesn't look like the load address anyway. Is that the load address? Let's go back up real quick. No, it's looking like that was the load address. That is start 500 or 800. Let's try 500. Nope, well, neither one of those was correct. Give me one more moment. It's kind of big on the screen, so I want you to be able to see the font well, but it's kind of making it ugly for me to read. DC8000, I think that's the one I got, right? DC8000, no. DC8000, DC8000. There we go. That's what I wanted. So look what's happening here. You can see that there's a call to execve, and the arguments are being loaded in. So let me actually, let's look RIP and the offset in time, RB minus 70, RIP plus that address. So basically, if we were to get to this point where we actually paused execution on this address of the one gadget because we exploited it successfully, you would see that one of these pointers is pointing to /bin/sh. And then those other constraints need to be there. And then there's the call to execve. And that's why it works. So if I drop to a shell, let's go back and run one gadget one more time. And I want to see if we can check out one other one gadget. But kind of neat though, right? Like, again, the fact, if you haven't seen that before, it's crazy. Like, I remember the first time I saw this, like, you mean there's a single code sequence that pops a shell instead of having to write a big ROP chain? That's crazy. So let's try this E2386. E2386. That's really close to the other one. Yeah, there's a call to exec VE. That's not what I wanted either, though. One more time. Let's try that other crazy one at the bottom we saw. Come on. 106 EF8. 106 EF8. That might be too far. Yeah, I think that's wrong. So I think the offset's going to be messed up there. So either way, you get the point of the one gadgets, and we talk through the reason why we would need this. I'll go through that one more time since I kind of started looking at something else. We're doing a capture the flag, or we're exploiting a remote program. Doesn't have to be a CTF, and we've got the binary on our system, and we've got it working. We're able to exploit it, and we've identified something like a one gadget or a ROP chain with a relative offset we need. Got it working on our system. But the version of libc on our system is different from the one on the target. So how do we now determine what the remote target's version of libc being used is? That's our next thing here. So what we're going to do is go back to the whole free hook thing. So if I run this and we grab this address again, which we saw was free hook, and we say x/gx, paste that in, and we see it's free hook. So what we want to do is take this address and the name, the symbol name, and pass it to the libc database scripts for find. And don't worry about the address, because you might be like, well, why does it need the address? It's randomized anyway. It doesn't look at the load portion. It only looks at the lowest 10 bits or so, only the very end here, because the relative offset there within a certain page region is going to be what matters. So you don't have to pass the full address, but you can. It's only looking at the lower bits. So now that we've got this information, let's drop out. So we'll say exit, and we're going to say /libc database and find. And what I want to find is free hook and then that address. And we run it, and look at that. It tells us. It says that is where free hook is within one of these versions of libc. Some of them are going to be like 32-bit versus 64-bit. Like this bottom one here, that's 32-bit, and the one above it's 64-bit. So you might have to try. It shouldn't matter, but it's one of these guys. So what you would then do is look inside this version of libc, find and run one gadget against it. Then the address you get from one gadget is going to be the one that you put into your exploit when exploiting it remotely. So that's the key thing I wanted to get across in this stream. One more time. We're running a CTF. We're exploiting a remote system. We've got a copy of the vulnerable binary. We get the exploit working on our system. We find a one gadget or a ROP chain or whatever it is that works on our system. We've got the exploit fully working. We don't know what the remote version of libc being used is. So we use the libc database. We take what is leaked, in this case it's free hook, and then the address, and we give it to libc database find script. And it tells us which version of libc at that offset is free hook. And you win. Now you know. So pretty neat stuff. Any questions on that, or any other thing you want to chat about real quick before we wrap this one up? I think I hit most of the questions, but if I missed one, please let me know. But hopefully that's pretty clear what we just did there. Like if you take that and you combine it with the flirt signatures and all that, you can see how you're improving your CTF game. And all those teams that are in the top every year, you always see the same teams like Dragon Sec and PPP and all those guys. Our wives are mad or whatever. They've all got that stuff, right? They all know that stuff. You need it for DEF CON challenge, yeah. Cool. Well, I'll hang out for a couple of minutes. Like I said, hopefully that was helpful. Next week, what is it? Next week is a new Sony covering Ghidra. So that'll be our session next Friday. whatever that date is. I think it's is that the 9th? Yeah, the 9th. Is libc to Windows equivalent to kernel 32.dll? Um, I don't think that's really a direct comparison because the way that Linux works is a lot different on system calls and such. Like if you look at the old system call way, it was an int 80 was the system call, and you would load the system call number in the accumulator register and then the appropriate arguments to the right of that. Like you could go up and look at the syscall database. They're out there for all the different versions on ARM and also in regular x86, 64, and you can see what the static syscall numbers are and the arguments needed. And RAX always holds the syscall number, and that's the big difference between Linux and Windows, right? Linux has a static syscall table. Windows is different, which is why the Windows shellcode is so much larger. And that's why I covered export address table filtering not too long ago. That was showing you that shellcode always wants to access the exports table in kernel 32 because it's looking for get proc address so that it can resolve the address of any function so that it can then get load library and start loading libraries and resolving all the functions. And so that's why we saw the export address table filtering sets a guard page up on the exports table of some critical DLLs so that it can detect whether or not who's accessing the exports table is supposed to do it or not, and it's not coming from dynamically allocated memory because that would be shellcode in that case. The live and upcoming section of the channel says it's Jordan Williams. Is that this coming Friday? You might be right. Yeah, you're right. You're right. That's totally right. That is going to be our session on Binary Ninja, and he will be giving away a copy of Binary Ninja. So I'm going to tweet that out actually after we get done here, just so everybody's straight on what the session is for next Friday, and point out that we're giving away a license on that one. And yeah, a new Sony I think's coming up after that, the week after that. Cool. All right. Well, I don't see anything else popping up. Have a great weekend, and we will see you next week. Thanks.